So, Dr. Kirkland, thank you very much for your time. And also, it is a great honor to have you for this 18th Japanese Anti-Aging Society.
Thank you.
You are so famous in this aging research, especially the new concept of a senescent cell and the possibility of rejuvenization by the depletion of a senescent cell. Senescent cell was considered to be just inactive cells, but according to your theory and others, that the senescent cell is contributing to the aging and the inflammation.
Correct.
So, with your word, would you please explain this new field?
Sure. So, senescent cells are cells that have stopped dividing, usually, and they were first found in cell culture systems by Hayflick and Moorhead back in the late 1950s. What they found is that if you put human cells into culture, they can undergo a limited number of divisions before they stop dividing, but they don't die. And they can remain in a senescent state and a state of replicative arrest for very long periods of time. In the late 1990s, Eugenia Wang discovered in 1996, or at least she published in 1996, that senescent cells are resistant to dying, very resistant to dying. So this is extremely important. So in culture, these cells, you could do things to these cells that you can't do to normal cells and they would survive. For example, you can drop the amount of serum that they're treated with and they will survive for years under conditions that would kill normal cells in hours to days. So they're resistant to dying. Then in the late 1990s, early 2000s, a series of groups found that senescent cells also occur in vivo, in experimental animals. And Ned Sharpless, who's now head of the National Cancer Institute in the United States, discovered in 2004, at least published in 2004, that not only do these cells accumulate with aging in mice, but they also, their rate of accumulation depends on how long animals live. So if you do things like calorically restricting mice, or if you make mice that have deficient growth hormone signaling, Ames dwarf mice, these kinds of interventions which delay death and delay loss of health span also delay the time at which senescent cells begin to accumulate. So there was an association found between the rate of senescent cell accumulation and the rate of deterioration of health.
I see.
Then Judy Campisi and around the same time Daniel Pipers both discovered the senescence-associated secretory phenotype. That's that senescent cells, at least in culture, produce a range of pro-inflammatory mediators, cytokines, chemokines that attract immune cells, proteases that break down extracellular matrix, and a range of growth factors.
May I interfere that before going to the suspect of the phenomenon, around the time that Judith Campbell was talking about the senescent cell so many times, her hypothesis was, senescent cell is not a bad guy. Senescent is a good guy to prevent the cancer.
Right.
So, I think later on there's a concept shift. So would you please explain this?
I think Judy Campisi's and others' notion that senescent cells defend against cancer is still entirely correct.
Oh, it's still there,
yes,
still alive.
Yes. So senescent cells conform. There are a whole lot of things that can make a cell senescent in culture or in vivo. The kinds of things that can drive a cell into senescence include things that happen in cancer cells. So potentially oncogenic mutations, expression of oncogenes, changes in metabolic state that are reflective of what happens in cancer cells, exposure to DAMPs, that is, damage messaging signals. Other things like this can all make a cell decide to become senescent, as it were. They can enter the senescent fate. So cancers include cells that have DNA damage and have all kinds of other things that can make those cancer cells become senescent and make them stop dividing. So cancer cells themselves, some people believe, go through a stage of senescence before they have a second mutation whereby they escape senescence and become fully blown cancer cells. So the proliferative arrest is one thing that's important in stopping cancers from progressing. The other thing is that the secretory phenotype of these cells that Judy described would kill cells around senescent cells. So if there are senescent cells within a cancer, the secretory phenotype of these cells kills the other cancer cells around that senescent cell. So they act like what we call demon seed. They're cells within demon a cancer seed, that can kill the cells.
So it's beneficial for the survival.
It's beneficial for survival, and that's probably how senescence came about in vertebrates. All vertebrates have senescent cells.
I see.
And all vertebrates can get cancer. A number of invertebrates don't get senescent cells and don't get cancer, so they don't need them to defend against cancer. That's the sort of thinking. Now, what happens is if you get enough senescent cells forming, they will actually promote cancer development. So it's what you call a yin-yang kind of thing.
So I think it was good for a while, but later on it's bad.
Yes, as senescent cells accumulate, they overwhelm the ability of the immune system to clear them. So they accumulate even more. And then the things that they produce can actually cause spread of cancer once there are enough of them. So the cytokines they produce can cause problems with other kinds of cells that can make them tend to become cancerous. The proteases that they make can break down tissue and allow spread of cancer cells. And those proteases that they produce can also interfere with the immune system by cleaving off things like Fas ligand and other things that immune cells depend on. Furthermore, the inflammatory cytokines, once they're abundant enough, can actually downregulate the immune system. So IL-6 can prevent macrophages from migrating properly, and that can prevent macrophages from entering a cancer and destroying cancer cells. So there's a paradox. And also senescent cells produce some growth factors as part of their cytokine. As part of their senescence-associated secretory phenotype. So what you don't want to do is interfere with development of senescent cells, because this is a way of defending against cancer. So if you have mutations that decrease P16 expression or P53, because these are major mediators of senescence, you will cause cancer very early in mice. So you don't want to stop senescent cells from forming. But once they're already formed, many senescent cells may be precancerous cells. Senescence could be the same as stage 0 cancer. So these are cells that are harboring cancerous mutations that have made them senescent. So actually you want to get rid of those cells once they are formed, because they could have a second hit and become a cancer. So getting rid of senescent cells is a good idea. Stopping them from forming in the first place is a very bad idea.
I see. So make it simple that forming the senescent cell itself is a good thing, but accumulation is a bad thing. So too much accumulation can be deleted like a senolytic approach for the senescent cell.
Right.
That is your theory.
Yes, and also by getting rid of senescent cells, even shortly after they're formed, you're getting rid of precancerous cells.
I see. So I had a question that because the senescent cell is protective for the cancer, but now I understand the senescent cell formation itself is protective,
yes.
But accumulation is a bad thing.
Yes. So you either want to get rid of senescent cells or you want to stop them producing the bad things that they produce, but you don't want to stop them forming.
I see. So that's very clear. That's a very good learning for me. So now make it clear. And also there are a lot of approaches, like including quercetin or a lot of senolytic agent of the senescence. How do you think this approach, how promising is this for senolytic of the senescent cell?
Well, I'm a clinician as well as a basic scientist. So as a clinician, I've seen many things that look good in mice and are very bad in humans. So we have to wait and see, and the clinical trials are going to be very, very important. But there are a few things that give me optimism. First of all, in experimental animals, senolytic drugs are doing a lot of very good things, some of which are published and some of which are about to be published. The second thing that gives me some optimism is that many of the senolytic drugs are developed from pre-existing drugs that are already approved for use in humans or from natural products that are known to be safe. So safety could be less of a concern than with some other approaches that are completely untested. And the third thing that gives me some optimism is that aging mechanisms in general tend to be conserved across species, fundamental aging processes. Cellular senescence is conserved from fish up to humans. So that means to me that if you target a mechanism that's conserved across species, and you find there's an effect in mice, there's a better chance that you might find an effect in humans than if you're dealing with a disease like Alzheimer's, which does not occur in mice, and which you have to introduce artificial gene mutations in mice to simulate something like Alzheimer's disease. Right. So that is difficult to translate. When you have something that's the same in fish and reptiles and mice and monkeys and humans, there's some optimism that if the drug works in mice, it'll work in humans. But that remains to be seen. The clinical trials are just beginning.
So there should be several real drugs. Do you have some particular drug that you have in your mind that it has a potential?
Well, I think there are at least 14 senolytic drugs now that have been
14?
Yes.
Under development?
That have been published, and there are many more under development. There are a number of companies developing these agents. So the way they work is, I mentioned before that senescent cells are resistant to dying. That was found by Eugenia Wang in 1996. The way these drugs work is by transiently disabling their survival pathways that allow senescent cells to survive despite the fact they're producing things that kill the cells around them. So in a way, what they have is shields, like in Star Wars,
right,
that prevent them from being damaged. So they've got these pro-survival pathways that protect them from committing suicide because of the things that they are producing themselves that kill the cells around them. So just a very brief disruption of any one of these pro-survival pathways, or SCAPs as we call them, senescent cell anti-apoptotic pathway, SCAP, is enough to allow a senescent cell to commit suicide because of its own SASP.
I see.
And different senescent cells depend on different SCAPs. There are at least 7 of them. 6 have been published. There's another one about to be published. And different kinds of senescent cells, depending on the cell type they originated from, depend on different SCAPs to maintain their integrity, to prevent them from causing apoptosis of themselves. So the different senolytic drugs work on different SCAPs or combinations of them, and therefore will have distinct effects on different kinds of senescent cells.
So in other words, each organ has a different needs a different senolytic agent to delete that senescent cell in the organ?
It could be the case. It's more that there are specific cell types that depend on different SCAPs, and therefore you need different senolytic agents. For example, endothelial cells depend on BCL2 family members for survival. So if you target particular ones, like BCL extra large, which is a target of navitoclax or A1331852, that will kill senescent endothelial cells. But other cell types don't depend on that pathway at all, and some of them depend on more than one pathway and are redundant, so you have to target them with multiple drugs. So one of the things we're finding with senolytics is that the old-fashioned drug development paradigm of one drug, one target, one disease no longer holds. What we have to do is maybe use combinations of drugs or use drugs that hit multiple pathways. We're trying to target multiple pathways, so that is, we're using drugs that hit multiple mechanisms, we're targeting multiple pathways, and we're expecting multiple outcomes, because aging and cellular senescence is one of the key processes that drives aging, along with some others, is the main risk factor for the bulk of chronic diseases that account for morbidity, mortality, and health expenditures. So the theory goes that by targeting a fundamental aging process such as cellular senescence, you should be able to delay, prevent, or alleviate multiple age-related conditions as a group instead of one at a time. So again, with development of these drugs, we're no longer looking at a situation where we're using one drug for one disease. We're asking if one drug can delay, prevent, or alleviate multiple diseases and conditions, things like frailty or falling and so forth.
I think this is a field that the society needs, not only the specific disease curement, but also the prevention of the aging itself, eventually prevent a lot of age-related disorders.
I think I think prevention will take longer to get to, because you've got to prove safety and all of this kind of stuff before you can go to healthy populations. But certainly the initial use of these agents and the clinical trials that are beginning are for serious diseases, for people who are already symptomatic, where we know that cellular senescence drives those diseases.
Okay, which are the typical diseases you are mentioning at this moment?
Well, the kinds of diseases where these trials will begin are ones where there can either be systemic treatment with senolytic drugs, that is, taking drugs or combinations by mouth, or by local application of these drugs. So a local application might be injection into a joint for osteoarthritis. But the other trials that are beginning are for conditions like idiopathic pulmonary fibrosis. This is a disease that affects elderly individuals. It's fatal. There are only a couple of drugs on the market that aren't that great. The only real treatment is a lung transplant, which you cannot do in an 85-year-old. In mice, at least, these drugs are highly effective in alleviating dysfunction and progression of idiopathic pulmonary fibrosis models in mice, that is, bleomycin treated mice, which get something like human idiopathic pulmonary fibrosis. So trials, multi-center trials begun in that particular condition with senolytic agents.
Oh.
Other places where they're going to be used or where trials are beginning are in things like bone marrow transplantation, in people who've had bone marrow transplantation. So people who get bone marrow transplants from not themselves but a different donor have to have a massive dose of chemotherapy to kill off their own bone marrow and to kill off the cancers for which they're being treated. That chemotherapy causes massive cellular senescence throughout the body.
Yeah, it's a part of a GVHD.
Well, that's a different condition. That's when the marrow actually attacks the host that it's put into. But in people,
you're talking about different situation.
Well, in people who don't get GVHD, who don't get graft versus host disease,
even without the GVHD,
they get accelerated aging. And
yes, this is our hypothesis too. We love this hypothesis.
Right.
So actually, we have used the senolytic agent to the GVHD mouse model. It's very effective.
Yeah.
And we are very amazed.
Right. So one of the places where trials have begun is in people who've had bone marrow transplantation.
Oh, is that right? Oh, I did not realize that. So not only the GVHD, but also the total bone marrow transplantation.
Yes.
And to prevent the aging, accelerated aging itself.
Yes, because these people, 3 to 5 years after their bone marrow transplant.
Yes, we have noticed that the white hair of the cilia.
And they get diabetes, and they get frailty, and they get all kinds of other age-related things, and they get a lot of accumulation of senescent cells.
Oh, wonderful.
But
we had a difficulty of paper accepted because a lot of senolytic agent like a BCL2 attack is not only the depletion of senescences, but also it has an effect to the immunological function.
Right.
So the reviewer always think, it may be due to the immunological.
Right. But the nice thing about senolytics and the way they can be administered, and in fact the most effective way that they work, is to give them intermittently. So a lot of these drugs have fairly short half-lives, yet they work if given once a month in mice. And the reason for that is it takes 2 to 6 weeks for new senescent cells to form. So what we use in our mouse studies and are using in the clinical trials is what we call a hit-and-run approach. It's sort of like treating a bacterial infection.
Right.
The drug does not always have to be around. These drugs are not continuously occupying a receptor or affecting an enzyme. They're killing a cell population that takes 2 to 6 weeks to reoccur.
I see.
So these drugs can be given one day a month or once every 2 weeks or whatever, depending on the condition. So we found with alleviation of age-related osteoporosis, for example, in a paper that we just had out in Nature Medicine, the drugs could be given once a month. This was dasatinib and quercetin, the combination. And that actually worked better than giving the drugs continuously because you avoid side effects. And the drugs have an elimination half-life of 12 hours, yet they're effective at getting rid of senescent cells, allowing resumption of stem cell function in the bones so that new osteoblasts are formed that make new bone, and also turning off stem cell function of the cell type osteoclasts that destroy bone. You only have to give the drug once a month in mice. So we gave the drugs to very old mice once a month for 4 months, and they didn't just have their osteoporosis slow down, It was actually partially reversed, so they gained new bone.
Wonderful. Thank you very much. So the future is so promising, and I have a final question. Are you taking quercetin?
I don't think people should be taking these drugs themselves.
No, quercetin is not a drug. It's a supplement. It's in the onion or the apples.
I don't know the difference between a drug and a supplement. Digoxin comes out of periwinkle plants, or I mean out of plants. Vincristine comes out of periwinkle plants. These are all very, very dangerous drugs. But if you go and eat that flower,
but you don't think that eating apple is a dangerous thing, right?
No, I'm just saying until we know the effects and side effects of these drugs, and particularly the combinations of them, I think we should wait for the clinical trials.
Okay.
And
I will wait for the drug, but I will keep eating the apple.
Oh yeah, no question. Eating apples, I don't think is very harmful, or other fruits and vegetables that have senolytics in them, like strawberries.
Okay. Thank you very much again.
Thanks.
And it's a very good learning opportunity for me, and I think for the readers too. Thank you.
Thanks. And when you're doing it, I'd be happy, if you wanted, I'd be happy to